Welcome to another simple engineering snippet. In this instructional video, we review the Carnot cycle and work a simple example. I hope you find it useful. A Carnot engine rejects heat to a heat sink at 27 degrees Celsius. It has an efficiency of 30%. If the heat sink receives 837.2 kilojoules per minute, what is the power developed by the cycle? Also, what is the temperature of the heat source? Let's review the four processes that make up a Carnot cycle on a TS diagram, starting with isothermal heat addition. Recall that the area under the heat addition curve on a TS diagram for a Carnot cycle represents the amount of heat added to the cycle. The second process for a Carnot cycle is isentropic workout. The third process is isothermal heat rejection. Once again, the area under the heat rejection curve on a TS diagram represents the amount of heat rejected for the Carnot cycle. The fourth process is isentropic work-in. This completes the Carnot cycle. The area enclosed by the four processes represents the net workout, shown here in yellow. Now let's start the calculations. The heat sink temperature is given in degrees Celsius. Let's convert it to Kelvin. The definition of cycle efficiency is the difference between the heat addition minus the heat rejection divided by the heat addition. For a Carnot cycle, this can be expressed in terms of absolute temperature and change in entropy. The change in entropy for both the heat addition process and heat rejection process is the same, so it can be calculated only using the absolute temperatures for the heat source and heat sink. The cycle efficiency is known, and we know the heat sink temperature, so we can calculate the temperature of the heat source, which is 428.5 Kelvin. Let's calculate the isothermal heat addition. Again, the change in entropy for the heat addition and heat rejection processes are the same for a Carnot cycle. Taking the ratio of the heat addition to heat rejection allows us to solve for the heat addition since we know the heat sink temperature and the heat rejection rate. The heat addition rate is 1,196 kilojoules per minute. Note that since the heat rejection data is provided in units of kilojoules per minute, all calculated heat and work terms will also be in the same units. This is valid since the mass flow of the working fluid goes through all four processes. Now we're ready to calculate the work term, which is the difference between the heat addition and heat rejection terms. The calculations are shown. The work rate is 5.97 kilowatts. I hope you found this instructional snippet useful. If so, then please like and subscribe. Thanks, and have a great day.